Hello everyone, this is my presentation on VANET routing protocols. To start off, we're going to go over a brief overview. VANET stands for Vehicular Ad Hoc Networks, which are an on-demand mobile network. They're based off of mobile ad hoc networks. The network nodes generally consist of dashboard units or vehicles and roadside units or RSUs. VANETs are integral for the creation of an intelligent transport system. The main differences between VANETs and MANETs are that VANETs typically have a higher bandwidth and are less predictable topology. They usually have a higher mobility as well. Some of the apps that can be created through the ITS, or they're used within an ITS, are comfort apps, which include things like navigation or inter-vehicle communication, and safety apps, which include things such as collision warning detection and weather info dissemination. Alright, so the first article that I'm going to talk about today is Analyzing Cluster Routing Protocols Performance for Vehicular Networks. Quick overview of this. It first starts off with a literature review, where the author goes over problems to consider when talking about new routing protocols. Some of those problems would be things such as latency times, bandwidth overload, fragmentation, etc. VANET types that they go over in the literature review would be topology-based, position-based, cluster-based, geocast, and broadcast protocols. And then it finally ends up with a simulation. The simulation tested out several different cluster-based routing protocols, such as AN or artificial neural network, AMICAD, MOBIC, Approve, and lowest ID. The specifications of the simulation was that it was run, the geography was a highway. There was 30 to 100 nodes. The simulation software was NS2. The speed of the vehicle nodes was 90 to 130 kilometers per hour, and the variables that were tested were cluster head membership. So the results of this paper are, as transmission range was increased, it seems that artificial neural networks performed better at maintaining cluster head membership than all the other protocols. Same can be said about as speed was increased. It seems that generally speaking that artificial neural networks outperformed all of the other protocols, dipping slightly below Prove as speed was increased in one set of tests. Some of the contributions of this paper. The paper seems to test a variety of different cluster routing protocols in a specific highway scenario. It shows the potential of artificial neural networks to be used in a VANET setting. Some of the limitations of the paper. It gauges the test results completely on cluster head membership. It doesn't make any mention of things such as bandwidth overhead or packet delivery rate. Some of the open issues that I hope can be solved with future research would be it is a limited scenario, being just a highway situation. Hopefully future research can run similar tests in a city setting or a rural area. And also I found that the obstacles were not defined within the paper. It's unknown if this was possibly just a clear field or maybe a highway in a city, or any other such obstacles were never made mention of. So the next paper I'd like to talk about is analysis of VANET protocols for urban and rural area using QualNet Simulator. Quick overview. The simulations were run in QualNet. The areas were based off of real locations within India, one being a rural area and one being an urban area. The protocols that were tested were dynamic source routing, or DSR, optimized link state routing, or OLSR, ad hoc on-demand distance vector, or AODV, and dynamic MANET on-demand routing, or DAMO. The parameters that were measured within the test were throughput, or the packet delivery success average, unicast, the rate of successful delivery, delay, time, or the time needed for delivery, and jitter, or the change in latency. The simulation specifications were, for the rural setting, there was 30 vehicular nodes, 10 roadside units, and the speeds of the vehicular nodes were set at 40 to 60 kilometers per hour. In the rural setting, vehicles were 14, roadside units were 6, with their speeds being set to 30 to 40 kilometers per hour. Thank you. So the results of the simulation. OLSR performed best in both rural and urban scenarios as far as end-to-end delay, having the lowest delay times. DSR performed the worst in urban and rural testing. As far as jitter or latency change, OLSR performed the best in the urban situation. DSR performed worst in the urban and rural scenarios, and DYMO performed best in the rural situation. As far as unicast is concerned, DSR performed best in urban and rural areas. OLSR and DYMO performed poorly, almost in equal amounts in the rural situation. And then finally, throughput. DSR performed best in both scenarios, and OLSR performed worst in both scenarios as well. Some of the contributions of this paper were that the data suggests that the throughput is higher in rural areas, probably due to less demand on the network, while unicast was higher and delay is lower in urban areas. Some of the limitations would be that there are a lack of specifications in this paper. Things such as packet size are never mentioned, nor path lengths, which would have been interesting and useful to have made note of. Additionally, there are no hybrid protocols that are used within the study. They're all either reactive or proactive protocols. Some of the open issues I hope to see solved with future research would be the use of additional simulation software such as NS2 to verify the validity of results. There seems to be a strange basis I found for speeds. Being from a rural area and living in a city, I find it strange that the rural area settings speeds were slower than the urban areas, which I find that to be kind of inaccurate, but it would be interesting to see maybe different speed settings for each scenario and see how they would affect the variables. The next paper I'm going to go over is ACR, a cluster-based routing protocol for VANET. ACR stands for Adaptive Communication Aware Routing. A bit of background on this paper. The paper goes over reactive, proactive, and hybrid protocols. It then explains the processes of ACR and then proposes how to use that in a VANET setting. So a couple of quick notes on that. ACR uses intra and inter communication procedures. Each node receives an ID, or as they refer to it as a loco, based off of mobility and distance. Then it uses Hamming techniques to measure the similarities of nodes. Nodes are then clustered if Hamming distances are low. The ACR also makes use of roadside units to support back-end communication as well. The simulation specifications. The simulation used VANETs to work over OmNet++ in Sumo. It measured reachability, end-to-end delay, or ETE, and total traffic received. And the three protocols used were ACR, AODV, and DSDV. So the results of this simulation are, as far as reachability is concerned, ACR outperforms DSDV and AODV. In terms of delay, or ETE, ACR has a mediocre range performance, falling right in the middle of both of the other protocols in terms of delay. And then in terms of total packets received, ACR significantly outperformed DSDV, but slightly underperformed compared to AOVD. Excuse me. Alright, so some of the contributions of this paper. It does a pretty good job of breaking down the protocol process of ACR and then testing against a reactive and then a proactive protocol, ACR being more of a hybrid protocol. Some of the limitations of this paper would be that it has a limited use of variables. Things such as overhead or cluster head membership are never mentioned. Additionally, it is noted in the paper that RSU depends on or uses RSUs to help with back-end communication, yet it is not mentioned within the simulation if any or how many are used. Open issues that I hope are addressed with future research would be testing against additional cluster-based routing protocols. It'd be nice to see this ACR, how it would compare up to other protocols. And then, of course, different testing geography, such as rural area, highway, etc. Alright, so the next paper I would like to go over would be a comparative study on routing protocols for VANETs. Quick overview. This paper tests efficiency of dynamic source routing, or DSR, ad hoc on-demand distance vectoring, AODV. It also utilizes fading models, such as the Nakagami M model, and then the Rayleigh fading model as well. This simulation was run using NetSim 10.2 and Sumo. The tests were run at three different speed parameters of 20, three different node parameters of 20, 40, and 60 vehicle nodes. Additional simulation specifications would be variables that were tested were average throughput, packet delivery rate, or PDR, collision ratio, or CR, end-to-end delay, or EED, and then overhead transmission. So the results that came out through their simulation, as far as throughput is concerned, DSR with the Nakagami M model and Rayleigh model performed better than all other protocols. AODV performed better initially, but then as time goes on, DSR performs better more consistently. As far as collision rates and packet delivery ratio are concerned, packet loss increased with greater traffic, with DSR suffering less loss. Conversely, delivery is typically higher with less traffic. DSR had higher delivery rates in 40 and 60 vehicle node tests. However, DSR performed worse than AODV in the 20 vehicle test. As far as delay and overhead transmission are concerned, DSR had less delay overall. Both generate large amounts of overhead as vehicle numbers increased. DSR generates slightly less overhead, though, overall. Alright, some of the contributions of this paper would be that it does a very thorough testing of DSR and AODV. It utilizes different vehicle numbers and even incorporates fading models. It shows the general benefits of adopting DSR as compared to AODV. DSR typically outperforming AODV in almost all test specifications. Some of the limitations of the paper were that it maintains a constant speed variable for the nodes. It may be outside the scope of the paper, but I do believe that changing the nodes and making note of how the variables change would have been useful. It mentions the use of RSUs in the test, but then it never goes on to specify how many are used, which is a strange oversight in my opinion. Additional open issues that I hope are solved by future research would be that AODV was used rather than DYMO. When I was doing further research into this, it seems that DYMO was developed as a successor, quote-unquote, for AODV, but I believe the authors went with AODV as it is a more developed protocol and is probably more common and known to people at the time. It is also a singular environment that is tested. Like many of the other open issues with the tests, I do hope that future research will go on to run these simulations with different environment settings. Okay, the next paper I would like to talk about, and my final paper, is a baseline for context-aware system for safety messages dissemination in VANET. Overview of this paper. It uses the slotted one persistence and traffic adaptive data dissemination, or TRAD protocols. Quick little brush up overview on those protocols themselves. Slotted one gives priority of retransmission to furthest node and has an adjustable default slot setting, which changes some of the parameters of the protocol itself. TRAD uses an adaptive beaconing system and assigns roles to nodes depending on their position. This paper itself seeks to solve the issue of broadcast storms being when the network becomes overloaded with requests during specifically usually instances of traffic update management, collision detection, etc. Some of the specifications of this simulation. The simulation was run in a real intersection, or a real-world intersection based off of Santiago, Chile. It was a two-lane, three-lane, four-way intersection. The researchers took the extreme densities of traffic, i.e. 15.6 in 73.4 vehicles in low and high density instances respectively. They looked to measure the variables of packet delivery rate, or PDR, dissemination speeds, or how quickly messages can get to all of the nodes in a specific area, and the delay times. They used also multiple beaconing frequencies within the tests of 2 Hz, 10 Hz, and then 10 Hz with wave service advertisements, or WSA. Alright, the results. First up, slotted 1 persistence. Slotted 1 had a significant drop-off in PDR and it had higher delays with the slot settings set at 2 and 3. It did perform better in a few specific instances. It had a better performance at 2 Hz and 10 Hz without the WSAs, with the slot setting set to 7 as well. The results for TRAD. TRAD performed better overall than slotted 1 persistence in almost all the tests. The authors do make note, however, that it is a more complex system to integrate. It requires a larger communication capacity, which would mean a greater amount of overhead within the network. Some of the contributions of this paper would be that it shows that TRAD has a potential to be used to counter the issue of broadcast storms. Additionally, it does a thorough testing of specific instance of broadcast storms. Some of the limitations of this paper would be that overhead is mentioned several times, but is never listed out thoroughly or explicitly within the paper itself. Additionally, the tests were run on the outliers of traffic, i.e. the highest and lowest densities. It would be interesting to see what the test results would have been at more of a mean traffic density. Additionally, the open issues that I hope to see solved with future research would be that tests involving more RSUs. Again, like many of the other papers that I have reviewed before, there was no mention or use of RSUs within the paper. And then additionally, like always, different scenario tests. This is a very specific instance and scenario, being a real-world intersection in Santiago. It would be nice to see how these protocols perform in settings such as highway, rural area, different city intersections, etc. Alright, so now we come to the end of my presentation. So in conclusion, VANET has many different situations and unique problems that face VANET that may require many different types of protocols. As we've seen, certain protocols perform better in certain specific instances, so there needs to be further research into how all of these protocols perform in all these instances, so we can make better use of them for specific applications. Additionally, further work needs to be done in developing protocols with lower parameters of overhead, better packet delivery rates, lower delay times overall, just making a more efficient network of things. And additionally, as always, there should be a precedence for real-world testing. Of course, in most testing instances, real-world would be too expensive and highly impractical. But if we are going to put things into a real-world scenario, they may come up with problems that you cannot predict for in a laboratory setting. And these are all of my sources, and that was my presentation. Thank you very much.